Okay, hi, good evening, everyone. Dr. Ho here. Glad to see everyone here. Uh, Expecting about 14, but with 10 of you here, 9:33, I think we respect your time. We just get started now. Today is not really a class. It's just more of like an introduction, walking you through the ULearnX platform, and then just taking any kind of question or concerns. And for about 6 of you, it's your first time with UTP and first time on this open distance learning. So you just describe a little bit the process, and for the rest of you, just walking through the content that we will have. So just feel free to interrupt me when, and if you have any questions and things like that. All right. Okay, so this is what you would actually see on your ulearnx.utp.edu.my lah. So for some of you still having, we're still working on your registration, your enrollment. You're not going to be able to access this, but either get through your friends, or you can also let me know. I can pass you what I'm able to pass lah. So like, for example, I've distributed this textbook as well as this study guide lah. Really what this is our website, where you can click on this, and this actually tells you kind of the whole plan of the course, what is kind of the main topics, and all that. What's the course outcome? What do we expect that you would learn at the end of it, right? So this is what we call the course learning outcomes. So there are just three main ones, and the goal of this course really is, number one, I'd like you to be able to evaluate for any kind of digital circuit, digital systems in VLSI. Just be able to estimate the speed of that, right? That's the key role here. And then not just estimate the speed, but with respect to what we call the modern transistor process technology. So one of the key things in this class, we'll look at a realistic model file, something that you would probably get characterization from a fab. Your circuit will be expressed in terms of these logic gates, and then how do you actually do back of the envelope, or maybe some kind of simple coding to estimate the speed of your digital circuit. And then the reason for doing that is this is all ideal, but one of the main drawbacks today, the main challenges in digital systems design and VLSI, is the effect of process variations. So if we were to try to make fabricate a transistor today, fortunately or unfortunately, your transistor will have a lot of variations. Like even the doping, I think we're down to at 7 nanometer kind of thing. You're down to 2 or 3, a few dopant atoms only lah per transistor. So if you're missing one dopant atom, you're going to have a problem because the transistor parameter varies quite a bit. And because the dimensions are so small, the diffraction limit is actually along the order of 193 nanometer for UV, but now we are down to less than 10 nanometer type of sizes. There's a lot of tricks being played to really get the lithographic process to be able to match that, but it's not foolproof, it's not 100%. So what really is the main limiter of performance nowadays is what we call process variations. You have the same integrated circuit design, you make 20 of the same chips. All the 20 chips are not going to be exactly the same. They're going to have different sort of performance and all that. So how do we analyze that? How do we take into account the effect of process variations? Specifically, how will it impact the speed performance? And the other difficult and challenging situation is what we call the aging effect. That is, even though you've designed your circuit perfectly, you've got your best design and all that, the process variations will kind of fuzz it around. They sometimes can make you not meet the specs if you're not careful. That's why we're going through this course. And maybe if all that is fine, you have your IC, you've made 20 of them, all 20 of them meet specs and all that. But as you use them, as they are being used over 1 year, 2 year, 3 years, the device, the integrated circuit itself actually undergoes aging. It's a process of over time, the performance is degraded gradually. And also the goal of this course is to try to help you to analyze why does this happen? Where does this happen? Is there ways we can sort of estimate how bad the circuit will degrade. And once you can estimate and you can quantify, you can look at ways to actually improve the robustness of the circuit. So just three main course learning outcomes for this VLSI course. Now, this course is not a typical traditional VLSI systems design course. So if you look at the canonical textbooks from VLSI like 20 years ago by Professor Jan Rabai from Berkeley, or if you even look at New West, so yet some earlier books, uh, that's what people call VLSI. They will tell you about layout, they tell you about the transistor, the NOT gate and all that. So I've had some comments in the past offering of this course, and I try to explain to you a little bit why I'm taking this approach to cover these things for VLSI. One of the simple reasons is we are no longer at the stage where we are looking into very detail about designing single gates. So when you actually have a design, your design is expressed in terms of logic gates. Each of these logic gates, the fabrication house has already design how the transistors will look like, what their sizes, what are their properties, and they will give you several options actually for a NOT gate, a NAND gate. So all these collectively, they are known as the standard cells of a process technology. So standard cells because they are standard logic cells, standard NOT gates, and then they come in various forms, various sizes and all that. So the old style of VLSI looks at how do you design one or two of these standard cells, how do you lay that up and all that. That's less important nowadays because fabs now are a service. They are no longer in-house. Most of the engineers, the majority of digital IC engineers don't design the gates in the fabs. They actually just use them. They design the circuits and then they use the gates. So in my estimation, it is less important now for you to really understand the nitty-gritty of how to design the gates, but more important actually for you to understand, well, these are the services and the gates that the fab offers me. How do I actually evaluate and make the best use of them in my design? So that's why this course is designed this way. So it's not a traditional, we're focusing on layout because number one, back end layout, I guess there's some people there are some universities that are actually working on that, actually pushing on that. I don't believe in that because other universities they can actually do it, but even if you ask your back-end engineers, most of the layout is actually done automatically by the tool, and they only go in and fix the difficult cases where it doesn't meet spec. But having said that, there is some exercises here I'll walk you through. I'm just asking you to self-study. If you were just to look at West chapter 1, this set of questions here, they're basically asking you to use a stick model to actually lay out the gates, and then it introduces you to in a very basic way to what we call the layout rules. There are certain rules in terms of spacing and all that. You cannot put two kind of like wire connections too close together. There are rules on that. So in a real chip, those rules are really, really detailed. They are really, really thorough. There's a really, really long list of them. Here, it's not our intention to go through all that because machines and softwares do that much better than human beings. It's enough for you to understand that there are those rules. You can look them up in your work when and as you need them, but no more than that. And then you can look at the chapter for some examples of what the common rules are. But beyond that, I don't think there's too much uh, kind of value into looking at that. But of course, we're going to take a survey on the MOS current voltage relationship. Okay, before I jump a little bit deeper into this, that's just by way of a introduction of the topic. Is there any question from anyone or any comment, or you want to know anything about this course? Do you have any expectations coming to this course? Is there something specific that you want to learn? Yeah, so just feel free to unmute your mic and let me know. Let's have a discussion if you like. I guess not. Okay, never mind. Still shy. So I think some of your friends, they will know that I like if there's feedback, it's back and forth, because it's not a one-way download. Your master's students, and especially for open distance learning, all the downloading actually happens when you watch the videos, read the textbook, but we will have a limited number, not too many synchronous sessions like this, where you ask me questions, I try to answer your questions and help you really understand. So that interaction is very important for me to help you to understand, because that's not, I mean, if you could understand it, you would have already understand it from the book and from all the exercises and the videos. And if you don't, then that's where these sessions would actually come in useful. Okay, so no matter. So this is the Ulearn X site. It's got a ton of material and videos here, and usually I'll put up the assignment here. This is actually last offerings assignment. I'm going to change it a little bit because I've kind of modified the content a little bit, and I'll walk you through it. But first, I just like to point you out there are several sections to this. I would recommend using the West and Harris textbook. It's one of the best textbooks I've seen around. It's very extensive textbook. We're only going to be using about 3 chapters of this book. I think it's chapter 1, chapter 2, chapter 4. Yeah, but feel free to read chapter 5, chapter 6, and the later part of the chapters, it will actually teach you about digital systems design, digital design, the different parts of the entire IC design and fabrication steps is covered in this excellent textbook. West is a very established, very well-known old professor. He's written the first VLSI book, I think, in 1970s. There are about, so this book has been updated by Dr. David Harris, who's a kind of a test and debug expert in Intel. I don't know what he's doing now, but those days he was there. No, he's a college professor. Yeah, he's a college professor at this moment. But he is a very approachable star. This is a book under the Wiley Plus library. You can only access this through the Ulearn X site. It is not a conventional textbook. It gives you a little bit more insight into what we call the process library, the standard cell library. It's just giving you different perspectives on that. And here I've given you several files on what is called the IEEE International Roadmap for Devices and Systems. This gives you a big picture, state-of-the-art view of the industry. Last time it used to be called the ITRS, International Technology Roadmap for Semiconductors. But starting in the year 2018, thereabouts, the industry figured out that they couldn't really just keep shrinking the MOSFET transistor, because the last 20, 30 years, the most of the progress in our speed, in our performance of our integrated circuits came from the fact that you could just shrink the size of the transistor. You would get twice the speed and 4 times the power saving, right? So it was an excellent kind of way. That's what has been driving Moore's law. But in around 2018, they figured out that it's not so easy to shrink the transistor anymore, and it became more of like a linear reduction only. Although I'm saying that, but since then they've still been shrinking the transistors. It's like 7 nanometer thereabouts already nowadays, right? I mean, back then when they were at about 180 nanometer, they were like, oh yeah, we can't go beyond the diffraction limit, but now we're at 7 nanometer. But this roadmap, from that point, they actually changed it into a roadmap for devices and systems. And there's sort of what is the more is actually giving you some thoughts about how they're trying to extend the Moore's law, that is to just kind of keep shrinking the devices. And I think one of the more popular is what we call FinFETs. These are what they call, sometimes they call it 3-dimensional transistor. The gates actually just folded upwards to kind of squeeze it. And beyond CMOS is actually talking about the technologies that are those kind of transistor, CMOS transistor potential replacements. So it's good reading just for you to get an overview. There are several more different kind of booklets on this, on different aspects of IC, on testing, on interconnects. If you're interested, let me know. You can actually get access to them through the IEEE. UTP has a subscription and all that. So it's just good reading for you. If you're in the industry and you're going to make a career in this for the next 20 years, something good to read, just to be aware that we're not always going to have CMOS nowadays. Starting this semester, we have something new. This is called the study guide or the self-instructional material. So it gives you a survey of what we will cover, the 3 course learning outcomes. And for this course, I'm keeping the workload reasonable. Not going to ask you to hand in homework every week and all that. There's going to be 2 problem-based assignments. So this is sort of like real-world problems I give you with the analysis and all that. They're meant to achieve all this. They're going to be 2 big ones. Conventionally, in the past year, I've asked the Intel folks to actually synthesize a RISC-V and then do the analysis on the RISC-V synthesized circuit. And then for the non-Intel folks, I give an easier circuit because it's not really going to be your bread and butter. This year, let me think about it a little bit more. Most likely, it'll still be RISC-V based. But if you have any special requests, let me know. So 40% of your coursework mark will come from these 2 assignments, 20% each. And then littered throughout the ULearnX site here, you see from module 1, 2, 3. There's some chapter and homework questions here from the chapter. This will I'll contribute about 10% of your marks. These homework questions are more just reinforcing the concepts. I just give you 10% for the effort. The final exam will be about 50%. And if you have feedback on this course, you can just fill out on this link here. And these are the textbooks that I've recommended. I'll try to add the links to the website soon. And I think I'd like to just draw your attention to this study schedule. Our semester is actually divided into 12 weeks. UTB follows a 3-semester system, January, May, September, 12 weeks in each semester. We are in week 1, and roughly I've given a guideline which chapters will sort of be covered and what sub-chapters will be covered roughly around that. And when should you, if you're trying to keep pace, when should you actually be finishing the homework assignments? When should you actually be working on the problem-based learning assignments? This is roughly for you to plan. This being open distance learning, if you want to learn faster, it's up to you. I will not stop you. I will encourage you actually, because maybe you have, you're anticipating some more difficult time at work in the future months. It's okay. If you want to learn slower, I would say be very careful about that, because if you fall too far behind, you're not going to be able to make it to master everything by the final exam. And I still also need to grade you on your coursework. So this forms a guide. Week 1 is this week from the 9th of May to the 13th of May. Of course, week 2 would be 16th of May to 16, 17, 18, 19, 20 to the 20th of May, so on and so forth. And your final exam will be somewhere between the 4th of August to about the 14th of August. You just find the 4 weekends, the 4 weekend days, Saturday, Sunday, the exam will be on one of those days, right? And then here there is a rough draft of 5 chapters. And I say it's a rough draft because this guided material is not your textbook. Let me emphasize, this is not your textbook. You're not going to learn a lot reading this, right? This is a roadmap. It's telling you the big picture of why you're studying this chapter, how everything relates, and where to go and do your deeper studying. So there'll be a mixture of textbook links as well as video links. So I have a bunch of videos also listed on the ULearnX here. So you can see here, module 4, the variable reliability. Module 3, you go in here, you click this, and then the videos are all here. And then you can click on the links at the bottom here. And then here is just, if you actually need the slides I used to create the videos, go ahead and do that, right? So there are videos to module 1, they are all here, module 2, module 3, module 2, 4, module 5. Some modules don't have videos yet. I think mostly mostly have lah, but I'm pending to make a few additional videos on aging lah. That will be done this semester. So you can follow all these videos, and occasionally I will give you some journal articles here for you just to enhance your understanding. Yeah. So like for example, here for logical effort, a lot of other additional materials. Here we are not yeah, they're just doing the path delay and estimation. Yeah, so there are some articles here, journal articles here, some slides here for you to review. Okay, but your guide, your starting point guide on what to read, what is the reference will come from this self-instructional material, where it's just kind of a big picture of how things link together and how where to find the resources, which chapters and all that. So I re-emphasize again, don't assume this is your textbook. This is not your textbook. This is just a guide. Where are you going to learn the material? We are learning from a variety of sources, textbooks, journals, videos, and all that, right? It's not no longer like undergraduate where you just read this section to that section and then you'll pass. I mean, that's not how learning is in the real world, all right? Okay, I'll just take a pause at this moment to check if there are any questions from anyone, if any comments. Am I talking too quickly? Did you get me? Did you not get me? How is it going for you so far? Today is not a lesson, it's just more of walking you through um, the um, the course, where to find the learning materials, what is the course all about, and how do you structure your time. Yeah. So any question at all so far?
Doctor, I have a question.
Yes, please.
Can you go back to the self-learning slide, the
Sure.
PDF?
Yeah.
I found out that the assessment mark, there's inconsistency there. So over
Systems.
here you can see that on the upper part you say that final exam is going to cost 50%, but the part that you showed just now
I
is
see.
only
Down here
40%.
is
Yeah.
the okay. Huh. Yeah, you're right. There's an inconsistency here. I'm mistaken actually. This part here is correct. Quantity of 2 primary assignments, 3 homework assignment, 1 final exam. Hmm. Okay. Let me correct it this way lah. Maybe you all go through it a little bit and you all tell me which one you prefer lah. I think final exam I have to give it. Uh, No, I think I still have the flexibility to give 40%. You tell me which one you prefer lah. You want me to give you more weightage on the homework or the problem-based assignment lah? Like I tell all past students lah, I'm a little bit, I guess, not conventional guy lah. I'm not trying to penalize you or make life difficult for you. My main goal is just that you get excited enough, you learn the material, and you take something valuable from this, right? Marks, I can give you marks. I can give you good marks and all that, as long as you learn the material, right? So what would be the best way to encourage you to learn, to help facilitate your learning? We can do that lah. So I started by thinking I wanted to assign heavier weight to the problem-based assignments and less weight to the homework lah. The final exam I'll check up. I think I think it's 40%, not 50 lah. The reason there's a discrepancy because I think before the COVID we were practicing 50%, but we had wanted to move it to be more heavy on the coursework so that you can accumulate most of your marks during the semester rather than in the final exam lah. Because you're a mature student already, so and then this type of courses, they are actually very hands-on skills lah. It's not, I mean, if I give you a 4-hour exam, how reflective is that going to be about what you have acquired and the real skills that you will use in your workplace, right? Especially in Intel. So I'm thinking that what actually matters more is like, okay, you can actually write some code or you can actually do some analysis, even if you take more than 4 hours. That's actually more important than being able to just cram everything in 4 hours lah. But now that we are no longer in MCO mode, everything is opened up already. I'm forced to give you online final exam lah. So in the during the MCO years, the last 2 years, your seniors, the people that came before you, they were able to take a 24-hour final exam, but we call that the extended assignment, and it was like an open book, everything open exam lah, but they had 24 hours to complete it. So we could make it very much more problem based. So we had like some design and things like that. But from this semester, last semester onwards, we have to give you 4-hour final exams lah. Your final exams will be conducted virtually, so you don't have to come to UTP, but they will require, the university will require you to turn on your camera and all that kind of things lah. So tell you what, Yihan, maybe I'll let you guys all like just browse through the site for a week or two. Then you tell me if you prefer to have more weightage on the homework assignments, which tend to be easier, or you prefer to have more weightage on homework assignment, or you want to have just a 10% and a 40% on the two problem-based assignments lah. Then I'll confirm with you again the final exam whether it's 40 or 50%. Is that okay, Yihan?
Yeah, sure.
Okay, thanks for pointing that out. This is I made mistake here lah, because this was just prepared. And if you find more mistakes, which I'm sure, I'm almost 100% sure you find mistakes in this stuff, because this is the first draft of this document lah. Previous semesters, this document didn't exist. That's why some of this you see here, I've got my notes here to insert a little more guidance here and all that lah. But if you're curious about this, if you don't find the material anywhere, feel free to ask me this in the WhatsApp, or you can also ask me it during our face-to-face, our sessions like this. So based on the schedule, actually, I've planned like these sessions are called synchronous discussion session. It will run between 1 to 2 hours there. For this course, I'm only going to have 5 actually. So it's not going to be too much of a time demand on you, but the downside to that is you have to be more proactive in your studying, and if you have problem with the material, you have to just really put in the WhatsApp and alert me lah. Are we only strictly limited to 5? No. I told previous students it's driven by you. If you really have a long list of questions and you really need a session, send me a WhatsApp in the group so that we can find a common time for everybody, and then we can add more sessions. So it's pretty much driven by you lah, right? So what I'll do in these sessions usually is I keep it free and easy. I usually have some kind of material that I just want to kind of review a little bit, talk a little bit about in case there are no questions, but the priority will always be to your questions. So my assumption is usually you've gone through the videos, you've attended the questions, you've read, and you're stuck somewhere with a specific example of a specific question or a specific homework problem, and we discuss that during this session. So it usually runs about 2 hours lah, historically lah, but the first session usually is 1. Today's session is not really counted as part of the 5. It's just more like an intro session. We can go until 10:30, or if you finish earlier, it's also fine. Or if you have more questions also, we can talk a bit longer. It's okay. So a little bit free and easy. And usually I would try to lock you in. So here is scheduled every alternate week lah, to cover the 5 session. But and I would try to just check with you whether are you okay on Thursday nights or do you prefer Friday nights. So if we can sort of agree on that, then I'll try to make it consistently on that. Unless something crops up, the majority of you are okay with changing or something, that would be fine. And this is not like undergraduate. You don't attend this session also, it's okay, right? Because this session is recorded. It will be put online on this Ulearn X. Specifically, I usually have a little section here. I've shifted it to the bottom. This is for example, this was actually the last year's classes example of that interactive session. So for today's session and future sessions, I will add them into interactive session, and I also give you access to the previous year's session, just in case our discussion sort of didn't really meet your need, or you were just curious what the previous semester studied. You can also go ahead and listen this, right? So for those very advanced, you just wanted to like listen to everything in the first 3 weeks or something like that, you can just go ahead and just listen to all these sessions. It basically would cover the span of those 5 or 6 discussion sessions we'll have. But every year is different because every cohort has different students with different interests, and you probably have slightly different problems to solve. So between one year to another, the sessions content will be slightly different, but not by much. The core is still the same. All right. Okay, so people who are very fast want to go ahead, you can just go ahead and listen to here. I will put in the sessions for our semester like somewhere close to the top here, somewhere here, or edit somewhere here, and then I'll put the date and time. So if you miss, you're not able to make it, you can always follow the recordings. You have the option, if you have questions, you can message the group directly. I usually will respond within the week, unless I see it's like very urgent and you're stuck with your homework or something, then I'll make an effort to respond faster. Either if it's an easy to respond question, either I'll just put a textual response, or I will record some kind of short explanation. If it's a bit more difficult, I will just propose a discussion session. Or if you have a list of questions, you can just put it in the group, and then you can also request, let's have a discussion session. We can go for 1 hour or even half an hour, and that's fine. So my practice, other lectures will be a bit different. My practice is I don't impose a fixed timetable. We keep it free and easy, but there are those 5 sessions roughly within every alternate week. We will schedule it. And if you need more, you let me know. If not, then, as long as you're learning, it's fine. Okay. So what are the materials? Here I put my grading rubric because the questions in this course are open-ended analysis and things like that. I don't emphasize too much on the final numerical value. It sort of really doesn't make sense to do that. It's more of the kind of process and the kind of analysis that's really the most important. So I give you an example of this is a rubric. Let's say the question has 50% marks. This is how I would grade. These are all the kind of the description of what you need to do in order to meet that particular grade. So 9 to 10 is clearly an A. Our UTP's A is 8.5 to 10. 85 marks above is A. 80 to 85 is A minus. 75 to 79 is B plus. I think 65 to 74 is B. And below that, I always forget because I think it's no point to tell students that if you're in like the C range, you have a very, very minimal and poor grasp of the subject, although you can pass. So UTP, for your masters, in order for you to graduate with your masters, you need to have a CGPA of 3.0 and above at the end of the whole program. That means you need to score on average, I think, above 65 marks for every course throughout the program, and then you can graduate. Now, what happens if you don't achieve that? Well, if you pass 40 for coursework and final exam, you will pass the subject. But if your CGPA falls below, you run the risk of not being able to graduate with the masters. So if, for example, you score above 40 but less than 65 for subject A, but subject B, you score an A, right? So if that counterbalance, you get your CGPA 3.0, you still will pass with your masters. But to be safe, you should aim to score 65 marks above for everything every semester, and then you'll be fine. Of course, if you can go for the A's, it's better. A is not that difficult to obtain, but it does involve some consistent effort, consistent reading, and you have to be really engaged and know your material. And it's not so much of studying and remembering stuff. It's being able to apply the analysis, being able to reason about what you've learned and apply it to practical situation, practical designs and all that. So this rubric is just for your guidance. Might tweak it a little bit. And here are 2 sets of videos. I try to give you a very brief introduction to the whole flow of VLSI digital design. That's the front end and the back end. This course is a bit more focused on the back end, but the back end part is very broad, so we're not going to cover all aspects. It's more of just letting you touch a little bit of layout, a little bit of looking at how the standard cells are characterizing, and mostly just how the effect of process variations and aging will affect the performance of your design. So it's just like after your design, your RTL is done, your Verilog coding, you've got your program, your design is done. This course will actually cover how is that translated to the actual gates that the fabrication allow you, and then how do you actually estimate the performance? In this case, it's speed. Okay, and then how does the process relations and aging actually degrade that? That's the focus of this course. So these are just flows. And I also give you a Docker container. Docker is one of these like virtual. It's like it's like a virtual machine, but it's a lightweight virtual machine lah. They call it a Linux container lah. But now you can actually install this on Windows. And the nice thing about this is you install Docker for Windows, you download this Docker container, you type this on the command line. The toolchain, the open source toolchain is pre-installed, ready for you already. And this toolchain is open source. It's not as powerful as the ones that you probably have at work and Intel and all that, but it allows you to convert any Verilog code into a synthesized design. That a Verilog code, high-level Verilog RTL code is converted into discrete logic gates. Those logic gates are mapped to the specific logic gates of your technology library, and then they are placed and routed. That means all the way down to the placement of the transistors and the wiring of those transistors. And if you can push a little bit, you can also extract the parameters of those wires, the resistance and capacitance parameters. I've given a little bit of example here, but maybe if I have time, I can delve a little bit more into it. If not, then you'll be at this level. And then the technology library is very important. Let's say you're making a chip. Normally, your team will actually say, okay, we're going to use Intel Fab, what process, or we're going to use TSMC in Taiwan, the Fab, what process. So that process, or sometimes they call it the process technology, it refers to the set of gates, logic gates that's available to you, and the Fab has a detailed characterization of that. Usually the model of those logic gates, the timing is given in a file called the Liberty file, .lib extension, Liberty. Here I am giving you two sort of Liberty file examples. In the code here, this is the Auckland State University, I think is a 350 nanometer process, 0.35 micron process. So the transistor's channel length is 350 nanometers, 0.35 micron. And there's another, what we call a speculative Liberty file like library. That library is for a 7 nanometer FinFET process. I would prefer if you can play with the 7 nanometer FinFET process. This is the one here at ASAP here. This is a link to it, because this Liberty file is much more similar to what you will see in a commercial environment, because it's got models at different temperatures, different process corners. We'll talk about process corners a little bit more later in this course, and also for different threshold voltages, also we cover in this course. So it's got quite an extensive, whereas if you look at the OSU 35 350 nanometer one, it is not so extensive, just a simple library put together with this open source tool. So you can just check that up. Okay, so follow all these videos. The first step is just giving you the high level extraction, how are logic gates put together from MOS transistor. So it's this idea of MOS transistor. You start by thinking about it as a switch. You use a network of switches, and with that network of switches, you can actually implement NOT gate, AND gate, OR gate, then maybe a multiplexer, NAND gate, NOR gate, and even other more complex gates, right? And then how do you lay them out, right? Because once you see how the logic gates are connected as, you see how the transistors are connected together as logic gates, you then can see how the transistors are actually laid out using stick diagrams onto the actual chip surface, onto the actual silicon wafer. Second, this is so important, the current voltage and charge voltage relationship of MOSFETs. Okay, we have someone joining in. Let me just add that person first. None? Okay, never mind. Why are you learning the current voltage and charge voltage? Well, number one, just to update your understanding of how a MOSFET transistor works. But more importantly is for you to see the relationship, how is current related to voltage, because we will be using your understanding of capacitance. Charge voltage is basically capacitance. Current voltage, current and capacitance. We'll be using this model to come up with what we call our linear delay model. This is basically a way to estimate the speed, the propagation delay of your logic design using a method known as logical effort, right? So if anyone just draws you a circuit and all that, if you have your technology library, you will be able to, within a few percent accuracy on paper, or maybe with the aid of a little bit of code, but actually you can just do it by hand on paper, you will be able to estimate the speed of this, right? And it's very powerful, right? Because not just you estimate the speed, logical effort will be able to pinpoint to you what is the reason this whole combinational logic chain is slow. Is there a possibility to speed it up? Where is the bottleneck? Right. So logical effort is very interesting because it's a linear delay model, but it will give you some insight into what is the fastest you can make this particular logic path and where is the bottleneck. And we'll talk about it a bit more later in the course. And if you didn't see it anywhere, note that down and then just raise it to me. Hey, Dr. Ho, you told me that you would tell, but I learned all this, but I don't see where it's happening, it's being applied. I'll explain it to you. Okay. Right. So that's the analysis too. That's why you are going through this kind of device physics kind of approach to understand the current voltage relationship and charge voltage relationship, because later on we will see number one, the current and the capacitance is basically the model how we're going to be estimating the speed. It actually comes from what we will actually abstract away the logic gates as RC networks, resistor capacitance network, right? So the current voltage relationship actually gives you the resistance of the MOSFET, the effective resistance, because resistance is V over I, right? And then the capacitance is actually charge voltage. So you have the resistance, capacitance, you use the RC constant, you can actually estimate the propagation time within a few percent. It's a very powerful technique, right? So that's why you're learning this. The second reason why you're learning this is to address the variability. So there'll be some equations in the West textbook that actually show you a sensitivity analysis. If the threshold voltage is changed by 5%, for instance, how does that change the drive current, the current of the MOSFET? And current of the MOSFET is linearly proportional to delay time. So from that process directly, you can estimate the effect of changes in the physical parameter of the transistor, the length of the transistor. Let's say there's a slight variation in that, or the threshold voltage, that there's a variation in that. How many percent variation will lead to how many percent variation in current and therefore in speed, right? So it will give you a direct relationship, a way to estimate in a quantitative way how process variation. So process variation means although you wanted a transistor with a certain threshold voltage, a certain length, certain dimension, it actually didn't actually fabricate that way because of the variations in the process. You should be able to quantitatively estimate what is the impact of this variation on the speed of the transistor, the degradation of that logic chain, that logic path, right? And we will also study more depth into this, what happens when you consider it as a statistical process, modeling it as a statistical distribution, right? And the same goes for aging. Aging also will actually degrade the threshold voltage, will degrade the drive voltage and all that. So that can actually be translated into a delay, in the additional delay in the propagation path. So the main message here is basically process variations, aging, they actually can compromise your circuit by screwing up the propagation delay of logic paths, right? And if it screws it up bad enough, it won't meet timing specs, and you get race conditions and all these kind of things, right? So this is the crux of the material. So the logical effort, you have to actually go through the theory of the estimate for a single gate first, then for what we call a logic path, right? And again, this analysis you're not going to do for every single logic gate in the design. What usually happens is you'll find out what is known as what we call the critical and near critical paths. These are the list of slowest logic path in your circuit. So when you do the synthesis and the place and route, the software tool will actually just give you a ranking of the top critical path from the worst case all the way to the best case. But that's why I provide this tool for you here, so that you can actually see this in practice. The software will spit that out, so and that you can actually trace that, you can actually find out what is that, what are all the logic gates on that path, and then you can actually apply that analysis there. Okay, And usually the assignment is a mixture. I get you to, most likely it will be something like, for maybe for a RISC-V or for a suitable circuit, you find the critical path, you just do the analysis in terms of the delay estimation, and then what are the bottlenecks of this thing. And then from that same design, the second assignment will be you will analyze the effect of process variation and aging on this and identify further weak spots in the circuit and propose how you can overcome them. Okay, so usually that's kind of the way it is. Of course, there's the ability for you to also use logical effort to estimate energy consumed by your circuit. And then this methodology also can allow you to actually pinpoint where is the hotspot, the culprit, and the gates which are consuming the most energy. And I'm not covering this anymore in this course, but logical effort is so powerful, you can actually optimize jointly for energy and delay. Joint energy and delay optimization, you can say for a certain energy, I want my circuit to meet this sort of energy consumption. What is the fastest I can go? Logical effort can actually give you that answer, but I'm not so sure it's so realistic for your situation, because for you to implement that answer, you need to have direct control of the size of individual transistor gates, transistors. And mostly in digital design, people don't do that unless in the old days they did that because computation was the bottleneck. That means, they spend a lot of time designing the adders, the multipliers. Today, nobody spends all those time anymore. Today, the main bottleneck is actually in communication. How fast can you get data to the compute units? So people pay more attention to the wires rather than to the logic gates, because the logic gates are fast, the wires are what slows things down. And we do have a logical effort way of actually estimating the effect, or the kind of whether the wire is the one that is actually the key bottleneck, or is it the logic gate that is the key bottleneck in the delay. This is the Wang paper here lah. Estimation and sizing of logic gates using modified logical effort with wire delay lah. And this is why I included this ability to extract the wire parasitics, the parasitic resistance and capacitance of the wire, because that's going to inform you on the sort of contribution of the wire to delay, again using RC model of circuits. Then towards the end here, just for fun, I give you some papers discussing FinFETs. FinFETs are supposed to be kind of like the intermediate between CMOS transistors to the next generation device. We're still not very sure what the next generation device is. Maybe some of you in Intel might have some insight. I'd be very happy if you can share with the class what you know. But this is just showing you what are the considerations for digital circuit design for FinFETs. How do you apply logical effort to FinFET? That's why I'm teaching this method, because it looks like it's actually a little bit more fundamental, can be applied to different device technologies. And this is actually describing that 7 nanometer FinFET process technology. So that would actually conclude the class, all of this material here. Okay, I'm just going to pause again to see if there are any questions. I know I might be saying a lot of things that are new and fast, but it's just meant, the goal here is actually meant for you to hear it once for the first time now, so that when you actually start your reading, your studying, see when you read it again, you more or less maybe can see where it might fit together in the big picture of things. And if you're still a little bit unclear about that, WhatsApp me, raise the question. Very happy to explain this again. All right. So if any comments, any questions on our course? In particular, I'd also love to hear from the non-Intel folks, because it's always a little bit of a worry. The Intel folks, I know what you need more or less. This is all fair game for you, right? Because it's going to be your bread and butter. Maybe your teams don't really think about this so deeply. I'm not quite sure, but my sense is from the past students that have taken this course, it seems it's quite new to many people, right? But it's very, very important, because beyond just doing the best design, this is actually the real practical reasons why the circuits actually can't go faster and all that, because it's a process technology, process variations, aging. These are the main problems in modern VLSI design. So yeah, actually, I don't see any non-Intel folks here. Well, that's okay. Yeah, I think Nazim is here. Yeah. So Nazim, if any of these seems a little forum, just feel free to reach out. It has its application because at the end of the day, any circuit, any chip or IC or electronic board that you will use in your industry, in instrumentation, will suffer from process variations, and especially importantly, will suffer from aging. So you must anticipate that no circuit lasts forever, and the longer you use it, actually the circuit tends to slow down. And for those of you who actually are used to, you have old computers lying around, like 10 years one, you realize that pretty much, like you used to be able to power things up within like 10 seconds, and then now it takes 20 seconds. You actually can feel it in computers and all that. Like the mobile phones don't last as long, so you probably couldn't tell. But if you are using it regularly, you also figure out. And why these are important now, this is because as the process technology goes to much smaller channel sizes, the gate length is much smaller, the effect is worse. So the effect of process variations, the effect of aging is worse for the smaller nanometer technologies than for your, let's say, a 1 micron. The 1 micron, pretty much you don't really have to talk about process variation, and you don't talk about process variations, you don't have to talk about aging and all that, because it's so big and so robust. It usually won't suffer from too much of these, right? So this is only because we are talking about the most advanced technologies. That's where it really will take a hit. All right. Any comments? Any questions? Any doubts? Sorry, Yanting, are you trying to say something? I can't really hear, but I see you've unmuted.
Hello, hello.
Yes, I can hear you now.
Okay, okay. How can I access the learning material?
Yours is a very difficult case at this moment, and if possible, Yanting, I'd like to talk to you for a short while after the course today. Once you enroll and register, you will be able to just log into UlearnX, utp.edu.my. You will be able to see this. If you can log into UlearnX and you don't see this, you need to let me know. If you've just enrolled, then give it at least 24 hours. But after 24 hours, you don't see, you let me know. Your case is special, Yanting. You will not actually be able to access it at this point. So what we've done is I've given at least the West textbook and the study guide to get started, but you will really need to get access to these. So the majority of you should already have access, with the exception of Yanting. So Yanting, I'll need to talk to you separately on this. Yeah. Okay, any questions? Okay, if not, then just kind of hang around for another 1 to 2 minutes. If not, then we can call it a night. I'll let you go. I will put up this recording onto the UlearnX site. If anything at all, just put it in the WhatsApp if there's any doubts, any concerns. As I mentioned, we probably will have our next session in another 2 weeks or so. Please try to really study and follow the material, because there's no point for us to have a session if you've not studied. I mean, it goes without saying, I'll just be talking, and you're not going to get the most out of our engagement. But if you're able to work on it, study at least even a little bit, you'll be able to get more out of the session by asking questions and just interacting, letting me know where's your doubts, if you have any problems. Okay, so just feel free to WhatsApp if there are any issues and any problems. If not, then yeah, you may actually log off now, and you're going to call it a night, and wish you a happy weekend. And I hope you are as excited to get started learning this material as excited to actually share it with you. So you're free to get started. Okay, for final exam, is it similar like PBL assignment? Yes, historically, my style is I try to give something very similar to the problem-based learning assignment, but it's going to have to be simpler, because it's only 4 hours. And actually, when I say 4 hours, the exam is actually designed for you to complete in 3 hours, because the fourth hour is actually for you to have log in and log out and any kind of difficulties in kind of like accessing any of the web stuff. So it's actually really a 3-hour exam. The exam is going to be open book, open notes, so you can reference everything, but you need to have your own computer, right? And you need to have a quiet spot, and your camera will need to be turned on, and you have to verify your identity throughout the exam. This is the UTP protocol. And you are not allowed to discuss with each other during exam, but it's open book, open everything. So that maybe seem like good news, but those students who have taken open book exams in our MSc will say actually is a bit more bad news. It just means that you're not going to be able to find the answer from the textbook. You're going to really have to understand and be able to apply it. But having said that, if you do well on the problem-based assignments, if you can do them really well and in a systematic way, you should have no problem with the final exam, right? Hope that answers the question is. Okay, great. So if that's the case, then okay, so we can call it a night. And maybe Yanting, if you can just hold on for a little while. Okay, sorry, EJ, you have a question.
Sorry, doctor, I would like to ask that is this a double pass course?
I'm sorry, a double pass course. Can you repeat?
Which means that I need to pass on the final exam and also pass on the overall.
Yes.
Okay.
Yes, UTP practices, you have to pass the coursework and you have to pass the final exam. Actually, you have to pass the whole thing and you have to pass final exam, which means if you pass the coursework, you pass the final exam, you pass the whole thing. But it's even more stringent than that. You should actually be aiming to get 65 above for both components. Then you're safe. If you pass, you really have to make up so that your CGPA stays above 3.0 in other courses. So effectively, I'm just saying you have to aim for 65 and above for everything, coursework and exam.
Okay,
it's
sure.
not that difficult, easier, but it does mean you have to put in the consistent work. Yeah. And I just repeat again, all of you are working. We understand that part of the open distance learning, the OTL program is we provide some flexibility if you face crunch time. So for example, if you know that maybe now it's May, maybe like in August you're going to have a tape out or something like that, and then you're not going to be able to sleep because you're going to have to be in office like for 13 hours, 15 hours and all that. You can let me know as soon as possible. What usually UTP, the mechanism we allow you is we allow you to take something called an incomplete. You can take the exam at a future time without additional fee, right? So if you fail, you have to retake the entire course. You have to pay the tuition fee again. Okay, but if you take an incomplete, you can take the exam at a later time, either 1 or 2 months after everyone else take the exam, of course, a different exam paper, or more likely we will let you take it at the next offering, but we don't charge you extra fee. You pass it, it's okay, right? So we will retain your coursework mark and we do that. So the incomplete is the way we can give you some flexibility if you have workplace crunch or you have some kind of family emergency and things like that. But the key is you have to let me know early. As soon as you know, I need a little bit of evidence as well, because I need to get this process started in UTP. Okay, so if you let me know and we can work it out, it's okay, fine. You have that option. Most of the students actually almost all don't really like it because it actually delays your degree program, but progress. But if you need it, that option is available. And also, if you really need it, if you need to take a semester off, we have the option for you to take what is called a deferment. That means you don't have to register or enroll in any courses for that particular semester. You also don't have to pay tuition fee because you're not enrolled in semester. But you cannot just not enroll, because if you don't enroll, UTP will assume you don't want to continue and then they will drop you from the program and all that kind of stuff. So you have this process where you actually have to apply. It's quite straightforward. The application, I think you just write a letter or email, and then there's an online form for you to fill out, and then they will let you know within a couple of weeks whether it's approved or not. That's just a formality. Most of the time, if it's a serious reason, let's say you've got serious work or things like that, you can also defer, right? So defer is like kind of the extreme case. You really cannot cope. You want to take a break for 1 semester, 2 semesters. It's possible. We have the process for it, right? So just keep these two in mind. I've had students in the past where they're not able to cope throughout the semester, but they tell me like one day before the final exam that they want incomplete and all that. I'm sorry, if you tell me one day before the final exam, I cannot help you. The UTP won't allow me to help you. But if you tell me some weeks before and all that, or if it's really an emergency, like 1 week before final exam, someone had COVID in the past, right? They told me I was already prepared already, but luckily that student was healthy enough. He didn't want to defer his final exam, so he sat for the final exam. He did well on the course and all that. Lah. So those kind of cases, yeah, you know, if you let me know as soon as possible, it's okay lah. But there's a case where the student had like, you know, like had to go offshore for 1 month, you know, and then one day before final exam told me, right? But you know, if you had to go offshore for 1 month, I was asked back lah, you know, cannot entertain lah, because the student knew he had to go offshore 1 month before, and then he could have informed 1+ month before that, and then we can actually process the incomplete. But the student didn't. I just waited until the day before the final exam, so I couldn't help that student, right? So just keep that in mind. Okay, any more questions? Okay, if no more questions, then I'm going to stop the recording here.